Section 9.6 of your textbook deals with the topic of graphing quadratic equations. Remember that a quadratic function can be represented by an equation having the form y equals ax squared plus bx plus c, in which a, b, and c are constants and a is not equal to 0. The graph of such a quadratic function is called a parabola, which is a curve that either opens upward or opens downward and is symmetric with respect to a vertical line, which is called the axis of symmetry. Looking at the two parabolas in our graph shown, the blue parabola opens upward and has an axis of symmetry that is the vertical line x equals 3, while the red parabola opens downward and has an axis of symmetry that is the vertical line x equals -2. The point at which the axis of symmetry intersects with the parabola is called the vertex of the parabola. Again, looking at our examples, the blue parabola has a vertex of 3, -4, while the red parabola has a vertex of -2, 9. Notice from the graphs that the vertex of a parabola is where the quadratic function has either its least or its greatest value. So it's often called a minimum point or a maximum point of the function. The blue parabola, since it opens upward, has a minimum point at 3, -4. And the red parabola, since it opens downward, has a maximum point at -2, 9. Now, in order to draw the graph of a quadratic function, it's helpful to be able to find the intercepts as a first step. So let's look at some quadratic equations and see how we can find the y-intercept and the x-intercepts, if any exist, for each equation. Our first example is the equation y equals 2x squared. Now, in order to find the y-intercept, we simply let x equal 0 in the equation, then solve for y. In this case, we get the simple equation y equals 0, which tells us that the y-intercept of our parabola is the origin, 0, 0. To find the x-intercepts, we would set y equals 0 and then solve for x, giving us the equation 0 equals 2x squared. That's a quadratic equation, so in theory it could have two solutions. There could be two x-intercepts for a parabola, but in this case there's only one, because the only real solution to that quadratic equation is x equals 0. Therefore, the x-intercept is also the origin 0, 0. And that makes sense. If our parabola passes through the origin, that point will both be a y-intercept and an x-intercept for that quadratic equation. In problem number 2, we have a quadratic equation where there's more than one x-intercept. Y equals -x squared minus 3x plus 4. Once again, to find the y-intercept, we simply let x be 0. In this case, the first two terms will disappear, leaving us with the equation y equals 4. So our y-intercept is the point 0, 4. We set y equals 0 to find the x-intercepts, and we obtain the equation 0 equals -x squared minus 3x plus 4. Let's multiply each term by -1, and then we can solve this quadratic equation by factoring the right-hand side and using the zero product principle to see that x is either -4 or +1. This means that the parabola has two x-intercepts. One of them occurs at -4, 0, and the other occurs at 1, 0. Our third equation is y equals x squared plus 5. Once again, it's easy to find the y-intercept. If we let x equal 0, then y is 5. So the y-intercept is 0, 5. And if we want to find our x-intercept, we let y equal 0. So we have 0 equals x squared plus 5, or -5 equals x squared. That's a quadratic equation that has no real solutions, which means that our graph has no x-intercepts. To visualize the graph, we would see a parabola that opens upward and never crosses the x-axis. Finally, let's look at a general form for the quadratic equation, the quadratic function, y equals ax squared plus bx plus c. And we'll assume that a is greater than 0 so that we can use the quadratic formula. In order to find the y-intercept, we again let x be 0, and the first two terms of the quadratic equation disappear, so we have y equals c. This means that for any quadratic equation written in standard form like this, the y-intercept is always the point 0c. For the x-intercepts, we have y equals 0, and notice that that gives us the standard form of a quadratic equation, ax squared plus bx plus c equals 0. So we can solve this equation for x using the quadratic formula. We'll get the solutions x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This gives us two separate values for x depending on whether the radical term is being added or subtracted, and those represent the x-coordinates of our x-intercepts. So our x-intercepts for any quadratic equation written in standard form like this will be the following 2 points. Negative b plus the square root of b squared minus 4ac all over 2a, comma 0 for the first x-intercept, and negative b minus the square root of b squared minus 4ac all over 2a, comma 0 for the second x-intercept. Now the intercepts are a good place to start when drawing the graph of a parabola, but they're usually not enough information to get a full picture of what the parabola looks like. So it's also helpful to be able to find the vertex of a quadratic equation when you want to draw its graph. So let's look at each of these three equations and discuss how we can find the vertex from the equation. In example number 1, we have y equals 2x squared. And remember in this case that there was only one x-intercept for this equation. When that is the case, when there's only one x-intercept for a quadratic function, that x-intercept must also be the vertex. So the vertex of this parabola is the origin 0, 0. However, when the vertex is not equivalent to an x-intercept, when there are two x-intercepts, the vertex has to actually be midway between the two x-intercepts. And this is because the vertex lies on the axis of symmetry, and the parabola is symmetric with respect to that vertical line. So it must exactly be halfway between the two x-intercepts. So in order to find the x-coordinate of the vertex, the simplest thing to do is to take the average of the x-coordinates from our two x-intercepts. You recall for the equation y equals negative x squared minus 3x plus 4, which is our second example, we found that our x-intercepts were at negative 4, 0, and 1, 0. So averaging those two x-coordinates, negative 4 and 1, we obtain negative 3 over 2. This means that the x-coordinate of our vertex is negative 3 over 2. In order to find the y-coordinate of the vertex, we can simply take our x-coordinate and plug it back into the quadratic equation. So in this case, we would have y equals negative 3 over 2 squared minus 3 times negative 3 over 2 plus 4. And with some simple arithmetic, we can obtain the y-coordinate as 25 over 4. If you want to verify that on your own, you can pause the video at this point and then come back to this. Now let's look at the general form of a quadratic equation again, y equals ax squared plus bx plus c, where a is greater than 0, so that we can find some formulas for the coordinates of the vertex. In the case of the x-coordinate, we would average the two x-intercepts. Well, remember that the two x-intercepts were given from the quadratic formula as negative b plus the square root of b squared minus 4ac all over 2a, and negative b minus the square root of b squared minus 4ac all over 2a. To average those two x-coordinates, we would add them together and then divide the result by 2. This looks a little bit messy, but notice that the radical terms in the numerator will cancel out. So the numerator of our complex rational expression simply becomes negative 2b over 2a, and that is being divided by 2. That's the same thing as multiplying negative b over 2a times 1/2. Now we can remove a factor of 2 from the numerator and denominator to obtain negative b over 2a for the x-coordinate of the vertex of a parabola that has an equation written in standard form. In order to obtain a formula for the y-coordinate of the vertex, we would substitute negative b over 2a in for x. So we have y equals a times the quantity negative b over 2a squared plus b times the quantity negative b over 2a plus c. Simplifying a bit, we have y equals a times b squared over 4a squared plus negative b squared over 2a plus c. That first term can be simplified a little bit further by removing a factor of a from the numerator and the denominator. Now if we want to combine our three terms, we would need a common denominator. In this case, the lowest common denominator for these rational expressions is 4a. So we can rewrite each expression with a denominator of 4a. The first expression already has that denominator. The second expression needs to be multiplied by 2 on the top and the bottom of our fraction. And the third expression, c, needs to be multiplied by 4a in both the numerator and denominator. Now that all these denominators are the same, we can add them together to obtain an expression for y, 4ac minus b squared all over 4a. So the coordinates of the vertex of a parabola that has an equation written in standard form will always be negative b over 2a and 4ac minus b squared over 4a.